I am too, but it should be you on my lap.
Today is a review lecture, so there is no potential test question for today. We're just preparing you for the exam. The exam, of course, is on Friday. I will not be here. I will arrange to have somebody here to proctor the exam. Just like before, please sit one person per table, not two people at a table. And it's, of course, not closed book. And
It's not. Wait,
it's not.
or excuse me. Wow, that was misspoken.
Oh, no,
It is not open book. It is closed book. No notes or
You
whatever.
should get Amy to proctor it for us, because
That's-
she'll give us all the answers.
That would be dishonest. My wife is not
I
dishonest.
know, but
How do you know that?
To proctor.
I'm just wondering.
I'll just move on and not because I trust and love her. Okay,
That's a good answer.
so we're covering chapters 20 through 24. So chapter 24, I have a whole lot of stuff here in chapter 24 in the review.
This is chapter 29.
Or 20. Wow. I'm just going to go home. You guys all read the slides. You
You know what?
don't have to take pictures. I'm going to post them to Moodle.
Because
They're easier to read on
We
Moodle.
like to get the notes in order.
and
They are
I
in
told
order
you
in
why I
Moodle.
take pictures last class.
Okay, so 4 basic elements comprise the vast majority of the Earth. That is oxygen, iron, silicon, and magnesium. And then you have 4 more that take up most of the rest, and that's nickel, calcium, aluminum, and sodium. Everything else is really minor components. And differentiation is that more dense things sink in less dense things. So when the Earth, even though the Earth is currently not in a molten shape or state, it's still, stuff will float up and down. So less dense stuff floats up, more dense stuff floats down. So we believe that we have lots of iron in the core, and you see that nickel, a lot of the nickel is in the core because it's more dense than other material. And so 74.3% of the crust is just oxygen and silicon. And so that goes kind of into what Hannah and I were, a piece of what Hannah and I were discussing before class. The vast majority of your rocks that are made of oxygen and silicon, because that's roughly 75%, right? 74.3% of the crust. Minerals are, yes,
Do we
great.
need to remember those, memorize those exact percentages?
No.
But do we need to know, like,
You should have rough
generally
numbers,
which-
yes.
okay.
Yeah. I mean, it's going to be multiple choice, and you're not going to have, is it 74.3 or is it 74.7?
Oh, so we do
Right.
need to know it's in the 74 range, though,
Yeah. Yeah, it's not in the 90 range, it's not in the 50 range.
but in the 70s.
Yeah.
Is that enough? That we just
Yeah.
use the 70s?
Yeah, if you have in the 70s, that would be enough to make sure you get it right. Okay, minerals, we learned about minerals. They're naturally occurring inorganic crystalline compounds. And some of them are useful to us for health benefits, some not so much. Some of them are toxic. And you have silicates, things that contain SiO2, the vast majority of your rocks, over 9% of your rocks. And then non-silicates, things like carbonates, oxides, and so on, that are a minor component for rocks. Crystallization, remember we had a homework question about which one crystallizes first. Now you're not going to have to go through and do the calculation for what percentage of silicon do we have. Right? That's not going to be something I'm going to require you to do on the exam for this type of question. But you do need to know that things with more silicate are going to freeze to lower temperature, so they're going to freeze later. So if I have a chamber of molten rock and it's slowly cooling, I'm going to form minerals that don't have much silicate first, and then the last ones to form will be the ones that are rich in silicate.
Things with more silicate freeze faster. Is that what you said?
Nope, the other way.
Wait, so things with
Things with less silicate will freeze at a higher temperature. Faster isn't exactly the right term, but first is the right term
Will freeze.
because it's cooling. And so, Hannah,
So you're saying that minerals are identified by the first sentence by crystal form and this fluid and fracture validity?
I am indeed saying that.
You don't need one.
Yeah, you don't need one, Bryson.
Oh, true.
Yeah,
I'll get one anyway for next day.
okay. Yeah, just getting ready for next Monday. Okay, so and many things crystallize in water if they're non-silicate. And that would be things like calcite crystallizes in water. Sapphire, as I told you, crystallizes in water. Rock types, make sure you know the difference in the igneous rocks, the ones that were melted and have frozen. And the difference in basalt versus granite is how quickly they froze. Granite froze very slowly.
Why
But
does
so-
granite freeze very slowly? Is it because it has more silicate?
No, because it's in a big underground chamber of rock. And so it's going to take a long time for the heat to get out of it. So that's why it freezes slowly.
Question.
Yes.
And the igneous, you have like the 3 different types of rock, or yeah.
I have 3 types. And of
Do
course,
we need to know those?
remember obsidian too.
Do we need to
Okay,
know those?
things that I care that you know is basalt, granite, and obsidian. I've said the word andesite, but I haven't paid much attention to it.
Salt is the C4 stuff, right?
Yeah. So basalt is a finer grain, but you still have crystal grains. Obsidian freezes so quickly that you don't have crystal grains. And granite freezes so slowly you have fairly large crystal grains.
So with that being said, like, do we not need to know any examples for the sedimentary and metamorphic?
Those are different types of rocks, so I haven't gotten to those. So for sedimentary rock, yes, it's on the next slide, actually, the stuff we need to know about it. Metamorphic, we just have to know what causes metamorphism, what you start with. Do you have a question, Bryson? No. What were you saying, Amber?
Nothing.
All right, so volcanoes. We talked about 3 different types, but we focused on these 2. Shields, where you have nice flowing lava, and so it just flows out and makes something that's fairly smooth, and that's what the Hawaiian Islands are made from. They're shield volcanoes. Or cinder cones, which is when you have lava magma that is pretty thick, doesn't flow easily, it builds up gas pockets, you have energetic eruptions, and that creates the distinctive shape of that cinder cone. And then composites are somewhere in between. So don't worry about the composite, just worry about the shield versus the cinder cone. And make sure you know things like Hawaii and, my brain goes to Grand Canyon, Yellowstone are hot spots. What's a hot spot, friends?
When to,
No 2s.
well, isn't it when they're like converged? No. Isn't it when
There's
a volcano
volcanoes.
is?
Okay, there are 2 people spoke at the same time. I didn't hear what they said.
Is it like a spot on a fault line where there's a lot of magma building up?
It's where you have a magma chamber that cuts through the crust.
Oh, that's
And so the crust can move over it. You don't have a boundary between 2 plates. It's punching up in the middle of the plates. Now, of course, you could have a boundary pass over the hot spot too. There's nothing that says that can't happen. But they're not at plate boundaries specifically. If they were, it would just be a random, unlikely coincidence. So this is the hot spot here. Well, it's a magma chamber that's creating this hot spot.
Like guys,
Well, the geysers occur, like a geyser, sure. The geysers occur with this because you're going to have, chambers of water here. And because of that very hot material, those chambers of water get very hot, and that causes them to spout.
Yosemite,
Not Yosemite, but Yellowstone.
Yellowstone.
In Yellowstone, yes, you have underground chambers that are heated up by the magma. They're not in direct
Is it like a
contact.
hot spot?
Yes. And so they're heated up by the magma, and they have the right condition where it can build up some pretty good pressure before it will break free, and then whoosh, big geyser, and then it goes back. Hannah.
Can we reiterate one more time what a hotspot is?
Okay, so a hot spot is where you have a magma chamber in the mantle. So that produces holes. So it punches holes through the crust and creates volcanoes where it punches through. And as the crust moves, it'll punch through here and make a volcano there. And then the crust moves and punches through there and makes a volcano there. And so it punches through different places. So it makes island chains, such as we see in Hawaii. We have a whole chain of islands. It's all one volcano or all one hot spot, and the crust is moved over and it's punched through in different places.
So a hotspot is basically a volcano.
Hot spots create
Volcano.
a kind of volcano. Yes.
Okay.
Not all volcanoes. Remember, that's what we did in lab when we had we simulated that by having the little bottle that was filled with hot water that had food coloring in it. And the hot water with the food coloring floats up into cold water. And that's the same as the magma floating up through the crust. And then when it gets to the surface, you have a volcano.
Thank you.
But that's not the only volcano. Don't just say, oh, that's volcanoes. Where's the other place that you likely find volcanoes? There's actually a couple other places.
Is it one like
Plate boundaries.
Okay, plate boundaries. Plate boundaries. When you have the plates coming together, that's a converging boundary. You're going to have subduction sliding underneath, and the grinding that melts rock, and the molten rock then floats up and creates volcanoes. That's not a hot spot, right? That's a completely different thing. It's still creating molten magma chambers, but it's not molten magma coming up from the mantle. Or if you have a divergent boundary, you do have magma coming up at the divergent boundary. Boundaries go apart. You're going to have something that comes up. So you also can have volcanoes there. Okay, continuing with the rock, because we're not technically on plate tectonics yet.
Can you go back to the other slide? Okay, I didn't get the word.
obsidian?
Yeah.
Okay, the sedimentation process, once again, just go back to our walk. We talked about weathering. Weathering is breaking up material, whether it's done by mechanical weathering, which is what happens when we walk. If it's done by chemical weathering, acid rain, we talked about in the chemistry section, will cause chemical weathering. Water will cause weathering without the acid, but not at as high a rate. Erosion is transportation, moving the weathered material from one location to another. Deposition is dropping it at the new location. And then sedimentation is the process of that deposited material getting compressed and becoming a rock, being lithified, as we said. Now, where are you going to find fossils? What kind of rock are you going to find fossils in? Sedimentary. You're going to find sedimentary rock because that's where the rock is being laid down. If an animal lays down and that rock is laid down on top of it, it gets compressed, and that's how we form fossils. So fossils aren't formed everywhere. They're only formed in regions where you have active sedimentation.
Isn't metamorphic rock formed from high pressure too?
Metamorphic rock is. It shouldn't say that here to be on the next slide. That's not the lithification process. That's a changing of the rock because of high pressure and temperature.
So a literal chemical change because of high pressure.
Sometimes there are chemical changes. It doesn't have to have a chemical change. It can just be a physical change, making it swirl like with marble. Okay, so sedimentary rocks are classified by the grain size. Remember, Hannah asked, so do we just need to know sedimentary rock and not any types? Well, you should know they're classified by grain size. So you have conglomerates, things with fairly large pebbles. Breccias, the only difference between a breccia and a conglomerate is breccias have sharp edges. Conglomerates have rounded edges. If we have rocks rolling down a stream, it's going to break off the edges and make them rounded. So conglomerates generally are formed in a stream situation.
Can you spell those on the slide?
And what is that for sedimentary?
Yes. And then you have sandstone.
What do would you like us to know?
I'm just going to go from sandstone down to, let's say, slate.
So we need to know those rocks.
You should know that those are all sedimentary rocks, and the difference in them is the size of the grain. I mean, you also have mudstone and a few others, but the size of the grain is the difference. Sandstone, of course, has reasonable sized grains. Conglomerate is bigger than the size of sand, and we'll just go with slate is smaller than the size of sand.
So sandstone, can you repeat sandstone?
Yes, it's sand
And a stone.
that's been turned into a stone.
But
so-
like, is those the ones that like can, like if you touch it and you like have enough pressure that it will break apart? Yeah.
Well, a lot of sedimentary rocks will do that. But sandstone has sand-sized grains in it.
So is this in order of,
This is in order of, well, these two are the same size. They're just, one's rounded, one's not.
So this is highest side.
Yeah.
Highest grade side.
Largest on the top, smallest on the bottom. Okay, metamorphic rocks. Notice there's the answer to your question. You do not need to know the difference in slate, schist, gneiss. Actually, I said slate on the other one. Now I have slate here. So slate is metamorphized mudstone. I guess I
So
should.
we don't need to slip. Oh, we don't
Here,
need to
I'll put mudstone instead of slate. And non-foliated marble quartzite. But you do need to know they form under high pressure and temperature. And the rock cycle. You have molten rock, magma. What's the difference in magma and lava?
Where it is.
Where it is. Lava if it's above the ground, magma if it's below the ground. Otherwise it means the same thing. Igneous rocks are when you have magma freezes. The sedimentation process, we've just gone over that. It has the weathering, the erosion, the deposition, and sedimentation. And then we have the sedimentary rocks. Metamorphic rocks could be either igneous rock or sedimentary rock that get metamorphized. And just like also the sedimentation process could come from any of the three types. You could erode a sedimentary rock, an igneous rock, or a metamorphic rock, and then have it go on with the sedimentation process. So make sure you know that rock cycle. And we sometimes try to draw graphics that have things like, magma, igneous, and arrows. The problem is it's very convoluted because any kind of rock can become sedimentary rock, and any kind of rock can become metamorphic rock. So it gets convoluted.
So if there's an igneous rock in sediment, will it just become sediment rock?
Yes, if you have a small little igneous rock that's laid down sediment, then you have sedimentary rock, and this little piece of sedimentary rock may be identifiable as igneous rock.
But
Right? If you have like a conglomerate,
technically, isn't sedimentary rock formed from magma anyway? Like, aren't all rocks formed from?
not all, over 90% are.
Yeah. But if all the crust becomes magma when it goes underneath, when it diverges, then wouldn't sedimentary rock be with the diving crust and turn into magma?
The rock, that sedimentary rock, is going to be melted, and so then it would come back reinvented as an igneous rock.
Even though it's made out of the same material.
So you don't differentiate if it's sedimentary, igneous, or metamorphic based on its chemical composition.
Yeah. All right.
Okay, chapter 21, the one where we talk about plate tectonics. Make sure that you know the layers shown here, the crust, the upper and lower mantles, the outer and inner core. So we have a total of 5 there. So make sure you know those layers and their order. And of course, the outer core, it's important to know that that's a liquid core. Inner core is solid. Yes.
Can you circle the layers?
Circle the what?
The layers, just so I know. I'm sorry.
The inner core is a liquid layer.
No, outer core is liquid. Inner core is
So-
solid.
That's the Earth's
That's the interior, right?
But never mind.
And how? Go ahead.
I don't want to.
You won't.
Yes,
Hannah, ask it.
No, I'm good.
How we know about these layers is by looking at seismic waves. So this graphic, I actually really like this graphic. It shows you the speed that's been determined by analyzing seismic waves as waves go through the earth. So here we have the crust, and you see the speed for a P wave in the crust is somewhere in the ballpark of 8 kilometers per second, whereas the S wave is somewhere in the ballpark of 5 kilometers per second. P waves are the faster waves.
Do
The
we
P-
need to know that?
Yes. P stands for primary or pressure. Primary because it's faster. It's the first one that you receive. That's why it has the name.
Go through liquid.
P waves can go through liquid. S waves, secondary waves, cannot. And that's an important distinction. That's how we know that there's a liquid layer. Because the S waves don't go through it.
Zoom back out.
Yeah.
Sorry.
And then the picture over here on the left, I'm afraid to zoom in.
You can zoom in.
Okay.
I just needed to get some of the words.
This here is showing how seismic waves travel through the earth. So if you're in the mantle, they just nicely curve. The reason they're curving is because the speed is changing with depth, and that makes the direction curve, what we call refraction. But then when we get to the outer core, the S wave disappears and there's a region with no P waves. So there's no P waves or S waves in that region because we had a distinct difference in the change in speed, a very abrupt change, which is shown in this diagram here. So it's this abrupt change in speed when you go to the liquid that makes it so there are no seismic waves that come in this region of the earth. And then we have only P waves in the remaining region because no S waves can go through a liquid. So this picture is built up by analyzing the waves. Right? We don't know what's in there and then we say what the waves do. We know what the waves are and then we determine what's in there. So P waves, primary waves. S waves, secondary waves. Primary because they're faster. Secondary because they're slower. So you can think of S waves versus the slower waves. But there's a physical difference that makes it so one goes through liquid and one doesn't. A P wave is also known as a pressure wave because the motion is parallel to the speed. So if a P wave goes from me to Bryson, the motion of the particles is going that same direction. That's what a sound wave is. A P wave is the same type of wave as a sound wave. Right now there's bursts of air coming out of my mouth and going toward you guys.
How are P waves generated?
How are they generated?
Well,
So if I have material like this and I hit it like this, I make a P wave go
it's
through
just
like that.
literally just like sound vibration.
Well, for earthquakes, it's physical motion.
It's just vibration, but it's in solid instead of in the air. That's the difference between it and sound, right?
Yes. I have two more question hands here, but let me do another one. That's how we make a P wave. For an S wave, I would have to take this and go like this. Right, so I push it like this, and then traveling this way would be S wave. I still have a P wave going that way, right? Yeah, S
Oh, I
wave
see.
going that way. Okay, so what was your question, Jose?
Well, because I was wondering, because like I've noticed that when there's like sound coming out of my phone speakers, it's like blowing at me. Like there's actual like wind.
What it's doing is it's pushing air toward you, then pulling it back toward you back. So it's moving both directions.
That vibration makes sound.
That's what our ears interpret sound. Hannah.
So primary means fast and secondary means slow.
That's right. And primary means the particles are moving the same direction as the waves travel. Secondary means the particles are moving perpendicular to the way the waves travel.
So
Yes.
for the inner layers, do you want us to know the difference between upper mantle and lower mantle, or you just want us to know that?
Know that you have an upper mantle and lower mantle.
Well, what distinguishes them?
What distinguishes them? The upper mantle is you have what's called the asthenosphere that's kind of mushy, And so the tectonic plates that move about are the crust and the upper mantle. And then the lower mantle is the part that it's sliding on top of. So that's why there's a differentiation there. And you can see, if you look at the speeds, that we do have some variation in the speeds that occur there at the Mohorovičić discontinuity, which is the boundary between the upper and lower. Okay, plate tectonics was devised by Alfred Wegener. People didn't believe him at first, but he said, look, if you look at the shapes of the continents, they kind of fit together like a jigsaw puzzle. And since they fit together, I'm sorry, let me get out of your picture. Since they fit together like a jigsaw puzzle, maybe they used to actually be like that, and they've broken apart. And of course, people initially said no, but looking at evidence, looking at paleomagnetism, that means looking at the frozen magnetic fields in soil. If you have an igneous rock, when it froze, I said soil, I shouldn't have said soil because that's broken up rock. If you have an igneous rock, when it freezes, any iron-type materials are going to be aligned with the magnetic field of the Earth when it froze. And so looking at old rock, you can look at those magnetic fields in the rock and determine the magnetic fields the Earth had at that time. And thus, they can draw pictures of how things must have moved. You have rocks with different orientations that must have rotated around. Yes?
Paleomagnetism is frozen magnetic rock.
Yes. And looking at fossil records. If you have the same type of fossils in two regions, you might assume that they were close together. It's not conclusive. But if you have, for instance, fossils on the continent of Africa that don't appear on the continent of South America, then you say these two must not have been in contact at the time when these animals lived, or the time that this layer was being put down. They could have separated and diverged. So it's using those that they have put together things like the video we watched about the plate motion and all the different supercontinents. Now, supercontinents, I have them on another slide coming up, probably the next one. You should know about 3 of them. Those 3 are Pangaea, which is made up of what 2? Yeah, that's the other 2 you should know.
Isn't Pangaea made up of the Cambrian and Precambrian?
Well, I'm talking about supercontinents.
It's not got Gondwana land either.
Gondwana land is one of them, and Laurasia is the other. So Gondwana land, it's on that slide. Gondwana land is what they merged together and then they broke apart again. And Gondwana land is what makes the African continent, and Laurasia includes South America as part of it. We've talked about the 3 different today in lecture we've talked about 2 of them: convergent, coming together with subduction; divergent, moving apart, creating a rift valley, putting in new ocean floor usually. The only non-underwater divergence or rift valley is in Africa. And then we have transform, which is what's going on with California and the Pacific Ocean, where the Pacific Ocean is sliding north with okay. For me, I had them in the right order. For you, I should go like this. The Pacific Ocean is sliding north with respect to California there. Other things that tell us that plate tectonics occurred are folding and mountain building and faults. So folds are what creates mountains. Faults are cracks that are created because of the stresses. So those are signs to tell us that this plate tectonics thing really has occurred.
What do faults do?
Faults are places where you have cracks in the crust.
But folds.
Oh, folds? Folds is like mountains. When you have, here is a good example of a fold. I take this and I compress it. Does that. Except for you have stuff down below, so it's going to go like that and make a mountain. Oh, goody, goody. Is there a way to hit stop?
So folds are mountains, what you said?
Folds are places where the crust has crumbled and mountains are formed because of those folds, yes. Chapter 22. shaping Earth's surface. Now, mountain building is part of shaping Earth's surface. Water, yeah, just go away. Kind of don't want to, yes, I want to quit. Cleaning up.
Well, we could do this on Thursday instead of
No. Okay, so
You honestly should do that. You should switch labs the Wednesday when there's a test.
I can't
Push
do
the
that.
test, the Friday test.
We don't have 3 hours during our class period on Wednesday.
Well, then just do shorter lab.
Okay, so we can still see the important things underneath Microsoft doing. It's my fault. I shouldn't have hit an update button a couple hours ago. I was just dumb. Fortunately, I don't have enough disk space. I think it stopped. Water is a significant factor in our lives. So understanding a little about water, that's important. So once again, facts we talked about on our walk a few Thursdays ago. 71% of the earth is covered with water. I mean, just remember 70, right? It doesn't have to be 71% to get it right. But more than 2/3 of the earth is covered with water. And 97% of all water on earth is salty. So that's not water we can drink. Of the remaining 2% of the Earth's water is frozen in ice caps and glaciers. We can't drink that either, right? Because it's in the wrong form and in the wrong places. So what we're left with is only about 1% of the Earth's water is water that people use to drink. I mean, unless you're in the right place, if you have glaciers nearby. And of that, only 1.5% of the remaining 1% is surface water. So when I look at things, like the streams, the rivers, Holmes Lake, yeah, that's a tiny, tiny little pond. All of those combined seems like a lot of water to me, but that's only about 1% of the Earth's water we could drink. The vast majority of it's in aquifers. Aquifers, underground lakes, not hollow caverns filled with water, but soil that's porous, it has holes in it that the water can be stored in. So your aquifers are essentially, I think of this as sandy soil that's saturated, filled with water. Saturated means filled with water, can't hold anymore. And so you guys, I'm sure, have different experiences than I do. But as a kid at the beach, I would dig down in the sand, and I noticed when I got to a certain level, I would hit water. And if I dug deeper, the water would just fill up to that level. Well, we call that level the water table. That's the level that the water saturates the soil. And if I dig down and I dig below the water table, it will just fill up. Now that was salt water. I wouldn't want that for my drinking water. But that's what the water table is where you have saturated soil. The hydrologic cycle, okay, so we spelled that wrong on the quiz question. I think we put hydraulic cycle instead of hydrologic cycle.
That's what messed me up. I thought that it was like water, the way it was spelled.
It is water.
No, but on the quiz, it was sun and gravity. But the way it was spelled, I was like, oh, it has to be water, and water wasn't.
It is water.
No, but Dr. Webb, you don't understand.
Look, the hydrologic cycle is driven by
sun
heat and gravity. Right.
Not water.
It is, but it's the hydrologic cycle.
No,
It's the
answer
water
is
cycle.
water.
Okay, another word would be the water cycle is driven by what? Sun and gravity.
I know what you're trying to say.
You understand.
So the sun heats up water and makes it evaporate. That evaporated water then is in the air, travels all over the earth, and it falls out of the sky in the right conditions. It should be falling out of the sky by the end of this week, either frozen when it hits the earth or liquid when it hits the earth. Both of those would be actually called precipitation. It's not just rain, also ice, snow, sleet. Those are all going to be precipitation where the water is falling out of the sky. But it can fall out of the sky anywhere. So it can fall on the top of mountains, and then gravity, of course, is what makes it fall. That's why gravity is the other thing that drives the water cycle. And when it hits the ground, either it runs off of the top of the ground, streams, of course, flood waters as we've seen recently, or it infiltrates into the ground, gets into the aquifer, into the groundwater. It may go into an aquifer, it may run out, an underground stream to some exit point. But that's our hydrologic cycle. It's really important. If we didn't have the hydrologic cycle, you would only have water in low-lying places. Now, something we didn't talk about at all, but that's important, when water flows through soil, it actually filters the water. And so groundwater is often really quite good to drink. Remember, groundwater means it's below the surface of the earth, in the ground. Good to drink because it's been filtered as it goes through the earth. Whereas if you have runoff like in a stream, you don't have that filtration, it's not necessarily as good to drink.
That's why spring water, you usually just drink it straight from the spring.
Yeah.
And you filter it through the soil.
But do note that we are saying usually, not always.
We just spring at my summer camp and we walk down there and get water.
Where's your summer camp?
In Ohio, can't remember.
So groundwater, water stored in the ground, porosity is a really important issue. If the ground is not porous, if we have a clay soil, the clay soil doesn't have nice pores that can store water, then we're not going to have a lot of water in the soil. Permeability is how easily water can go through the soil. You can have big pores, but if the pores are sealed off, then the water can't go through. So those two things are very important for the storing and transportation of water in the earth. The water table, I've already talked about, that's the level of saturation.
Do we need to know those in order?
There is no order here.
Wait, what was porosity?
I mean, I know they're by definition they're listed in order, but there's no special order. Porosity is the percentage of cavities you have to the entire volume.
Of the soil?
Yes. And so, for instance, you could have something like styrofoam. Styrofoam is highly porous. Styrofoam is almost entirely air. But styrofoam has a very, very low permeability because it has a whole bunch of air pockets that are trapped. That's why it makes a good insulator. But it doesn't work for having water go through it. So permeability would be about having these holes linked so that there's, okay, my picture doesn't show it, so that water can actually flow through the pores and not just be trapped. Artesian wells and springs are places where the water table, the level of saturated soil, is higher than the Earth's surface. And at first glance, or first blush, it seems like that should be impossible. But that's possible because you can have a a non-permeable layer between the surface of the ground and the water. And then the water can have a higher source up here, and gravity is compressing, so you have high pressure water under the non-permeable soil. If you dig a hole through that soil, or if a crack occurs, then the high pressure water comes up. That's what makes an artesian well or spring. Question? Well, artesian well, you dug it. Artesian spring naturally occur. Question, Hannah?
Are the problems that may occur related to the groundwater? Is that what that's saying?
What?
The point that says problems that may occur,
Oh,
is that relating to the groundwater?
yes, these are problems that may occur related to groundwater. The hydraulic head, let's actually not worry about the term hydraulic head. It's a measurement of the difference between ground level and the water table. So problems that can occur, subsidence. Remember I showed a picture from Central Valley of California where the ground level has dropped tens of feet, like a whole lot. I forgot what it was, 60, 70 feet.
Crazy.
Because of water being pumped out. That water helps to keep the soil so it has more porosity. You pump out the water and the soil can compact more, has less porosity, which means it's not going to fill up with as much water even if you have saturated conditions again. Carbonates can dissolve. That dissolution means they dissolve. Because carbonates, calcium carbonate, they're a salt. You put them in an acid, they're going to dissolve. Water has both weak acid and weak base properties, so it will slowly dissolve them. And so if you have moving water, it can wash them away, create underground cavities. Now remember, aquifers are not cavities. If you take out the soil, suddenly you have nothing supporting what's above. And oftentimes you will have the cavity collapses, making a sinkhole. If it doesn't collapse, well, then you have caverns or caves. So those are some problems that can occur, especially like I said in lecture, if you have a rare car museum that has a sinkhole that forms underneath it, and you have a vintage Corvette that falls into a sinkhole. Huh? Yeah, in Kentucky, yes, in Kentucky. What's your home state?
Kentucky.
Okay, so
I live an hour away from this.
oh, cool.
Not really.
Okay, streams. We learned about streams. You know, we really should have taken advantage and had a field trip to go out and just look at the Platte River when it was crazy. It probably still is kind of crazy.
That's what we should do tomorrow.
Yeah,
I'd be down.
we could do that tomorrow.
I might think about it. I will A, check on conditions, B, check to see if there's any students. How many students have a car?
You don't have a car?
Well, how else would we get there?
I
We're not walking.
I thought it was
Right
like,
there.
It has like this much gas in it, and it's not very reliable. Lots of-
Well, she has maybe.
yeah, I do.
And I could
But
take
I don't know.
5 people.
I'm not very.
You can take 5 over me.
I could take 5 and 6 yourself.
So between you and me, we could do it. So we can have enough transportation. I will look and see if that's feasible.
You have a minivan?
Yeah, it's just, that's my mom's school thing.
Oh,
We didn't
okay.
buy a new one, so yeah.
Okay, so stream flow. Deeper water flows faster because you have less friction between the soil and the water. And faster water will have more erosion, carry more stuff. So in our flood conditions we're having, we're going to have more erosion occurring because of the fast-moving water. Where the water moves slow, it's going to deposit that sediment. Question was in.
So like on homework, when it said if it was shallow water, what could happen to make it move faster without changing the depth of the water? So the correct answer would be if you like change the angle of it so it's steeper.
I have to look at the questions to make sure. When I finish the review, let's look at it, okay? Because I have to look at the wording to make sure I understand. So we have erosion and deposition that occurs with streams. And one of the things that is important to me is this, that you create meander valleys and floodplains. Valleys where the water has eroded back and forth and laid good sediment that we talked about, makes good farmland, but it's all pretty much at the same elevation. So if you have high water, it floods the whole region, hence the term floodplain. And yeah, I hope, actually, I didn't think about this until you suggested it. I hope that the weather and the flood conditions are still there so we can go out tomorrow, because that would just be cool. We could see this in action.
Well, if it's gonna rain tonight, then there won't be flood conditions.
Actually, our local rain here is not as big an issue. It's water melting and running down the streams that's really feeding all of this flooding. Right. We had hardly any rain associated with all of this flooding. It was all.
It's not.
It was because of rapid thaw. What was your
How far
question?
is the river access?
It's what, 30 miles for the round trip.
30 miles is not an hour. It is.
Yeah, I mean, if we go, we'll go to the Platte River State Park so we can go up on the observation deck and look out there. Don't worry, it'll be less than 3 hours.
Your kids will be fine, person. They will get to see you.
You should just tell your boss today that you may not make it.
Well,
Jennifer has other workers, doesn't she?
I assume he doesn't work
No.
during lab time anyway, right? So it shouldn't be an issue.
You would assume whatever you would like to assume.
We'll watch out when it gets up.
So,
That bridge when we get
The
there.
Continental Divide is the name for the division between drainage basins. We are on the east side of the Continental Divide. Basically, the Rocky Mountains is your Continental Divide. Everything on the east side of the Continental Divide is draining into the Atlantic Ocean or the Gulf of Mexico. Everything on the west side of the Continental Divide drains into the Pacific Ocean. That's what the Continental Divide is. And it's something useful to know. Once again, if you're going to be teaching grade school students science, knowing these things is good information to pass on to those students. When water goes from fast moving, such as a stream, into stationary, such as a lake or an ocean, it will deposit a lot of sediment, creating these deltas. Water going through mountains will create V-shaped valleys.
Wait, I have a question.
What's that?
How are oceans stationary if they have waves go through them?
The water's not flowing. You have waves, which is energy transporting through it, but the water itself is not having significant motion.
Wait, why do glaciers not completely melt?
Well, it's only a glacier if it doesn't completely melt. If you have a net growth or no net loss in a year, then it's going to stay around and it's a glacier. If it deposits snow and ice and then it all melts away, it's not a glacier. So it has to be
So
something
what
that
is
has some permanence to be a glacier.
What is it if it's not a glacier? Like if it melts?
It's temporary snow. You know, that's what we have here, right? We don't have glaciers here because it's not year round. So glaciers have an accumulation zone and an ablation zone. Ablation zone is where it has a net loss of material. Accumulation zone is where it has a net gain of material. Glaciers can flow if you have a change in altitude because they flow downhill due to gravity. And that flowing will create U-shaped valleys, which look different from the V-shaped valleys carved by water. They will grind up a lot of rock, creating moraine. Notice I crossed out the words esker, Drummel, and Till. You don't need to know those. And finally, sand dunes. We talked about how sand dunes are made with wind blowing. Goes up the side of a sand dune, and then when you get to the back side of the sand dune, the wind slows down, tumbles, and drops its sand down, building up the backside of the sand dune. Yes?
What was the difference between the two A ones?
The two A ones. What does that mean?
Accumulation.
Oh, accumulation is growth. Ablation is shrinking.
Can you give? Okay, so sand dunes. I'm not quite understanding how those are formed.
Okay, so the red here is wind, right?
Okay, so wind.
And just like water, moving wind is going to pick up a little bit of sand. So it's going to have a little bit of sand that's being carried in the wind. And then when the wind gets to the backside of a sand dune, it slows down. And when it slows down, just like water, it's going to drop it out.
But if it gets to the back of the sand dune, then how did the dune form?
How did what?
How did it form if it goes to the back of it? Like it has
Well,
to be there.
you have to have something to start a little ripple. And once you have a little ripple, then this process will make it bigger and bigger and bigger and bigger and bigger. Because it just keeps building up the backside. So you have to have something to make it start.
Okay.
And of course, randomness of nature means you always are going to have something.
So what's a moraine? Moraine?
Okay, the moraine is the ground up rock and soil the glacier produces, right? As it moves, it grinds up rock and soil. Okay, chapter 23 was geologic time. So we have relative dating and we have absolute dating. Relative dating is this is older than that. This is younger than that. And principles we use for dating. So these are all principles. That's a P. Second letter was R. The principles used to interpret is original horizontality. That is, you originally laid down horizontal layers. Superposition, the layers on top are younger than the layers underneath. Cross-cutting, if you have one layer that cuts through another one, the one that cuts through has to be the younger one. I mean, it's all of these are actually very logical if you think about them. Intrusions is actually material that has intruded into other material, so it's tied together with cross-cutting. Lateral continuity means that you should have the same stuff if you go, horizontally at the same level. And finally, faunal succession is that the fossils you see in younger layers were at a later time than the fossils you see in older layers, that you have a succession of the fossils. Now, for the absolute dating, we use radiometric dating. And remember, carbon-14 dating is a radiometric dating technique, but it's not one that traditional long age people consider important because it can only date out to about 50,000 years. So long age people are much more interested in longer dating techniques such as potassium argon dating, uranium lead dating, or strontium rubidium dating. For the geologic times, just know what's right here, okay? Just know what's in that box.
All of it?
Do we
Yes.
need to know?
That's a lot less than what we went over in class.
Do we need to know what goes with them, or just?
Yes, you should know what kind of life forms you have in each one of these.
And then how do we, is that in the book?
So, yeah. I mean, what dominated in Paleozoic? Think about lab.
Fishes,
Yeah. This is, let's just put things in water.
like the paleo,
And then the Mesozoic,
the lizards.
reptiles. And what's the most famous reptile category? Dinosaur, right. And then what dominates in the Cenozoic? So make sure you know that.
Paleozoic, is that water?
Paleozoic, it's things that live in water.
Okay, so water animals.
Yeah, it's not water dominated. Things that live in water dominated. I've already got the supercontinents. We're out of time. The last thing here is on the oceans, and so I have.
No, you were skipping so many slides. We cannot take pictures that one.
Good.
Okay,
Got that one.
got that one.
Wait. Okay.
This is what we talked about like yesterday,
See you later.
and that's it.
Oh wait.
Well, no, because this won't be covered on the test.
Oh, that one won't be?
Right.
Oh, that one won't be covered on the test.
Right. This is the last that will be covered on the test.
Wait, I had a question.
Go ahead.
So you did not have it on the slide. I did not remember writing it down.